Okay. Is there anyone who would prefer me to speak in English?
Конференция решено, что если доклад написан на английском, можете говорить по-английски. Вы выбираете.
Well, okay, I'll speak in English because for the benefit of the people who are our guests. I've actually have had a presentation here in the last session in the analysis. My name is Maxim Bakaev. I don't know if someone was in that session. These two are related, so maybe you will see some things that may seem familiar. And they are partially based on the same data, but the purposes are different, although they are both about the report. And our research was done together with our colleagues from Germany. They unfortunately could not put their name among the authors because the German government introduced some restrictions for cooperation with Russian universities. But my friends say that it's okay if I present it. So, just a second. Yeah. So, machine learning, as we know, of course, is based on regularities that are learned from data. And you, of course, can name the most universal approach in machine learning that usually solves all the problems. What is this? Any ideas? Well, you should have known. Just get more data. Get more data, and then everything will be correct sooner or later. Okay? But yeah, this is a picture I like, so I'm sure we can get it again. That 80% of all activities of data scientists or machine learning engineers is getting the data, labeling the data, structuring the data, cleaning up the data, and so on. And generally, you need millions of records. That would be fine, but they say that we are beginning to use up the data that humanity has created during its history, because ChatGPT-4 is said to have used up to 50% of all text available on the internet. So after a while, we cannot have more data because, well, not in every field, of course. For example, astronomy has still plenty, but still this problem in some fields start to emerge. So from the extensive development, we got to move to intensive development and hear more about data quality, which is my talk exactly about. So yeah, data quality is a very multidimensional concept. It has, from the literature, extracted over 20 dimensions. Not all of them are easy to measure, to quantify, I mean. And we all know from the here data-related conference that training data, especially for supervised learning, can be expensive because we need to spend effort to free people. If these people are students, that's better if these people got to be experts. For example, if you need to label medical groups, that sounds very expensive. And one of the reasons, of course, is that no one wants to spend their life labeling the data. That's not the most exciting task in the world. And also, several years ago, I saw in the newspaper that prisoners are made to label data for e-commerce in Finland. So it wasn't their choice, it was just the work they did. And also, of course, large companies are hiring people. For example, Yandex has recently opened a very large program for AI trainers, which are basically about being a human and being able to explain and evaluate things for the Yandex version of ChatGPT. So you might have heard that. And yeah, of course, not everyone is as rich as others. And many small companies, they do not hire in-house interns. They generally have to outsource this kind of task and don't want to pay lots of money for that. Well, the researchers, of course, even we have some kind of grant. I'm sure most of the grants, they do not imply that we can pay to data labelers. Maybe I'm mistaken. But usually this is not allowed, at least for Russian grants. So one of the solutions, which is new, has been around almost over 10 years, is the so-called microworks crowd labeling, crowdsourced labeling. That's when people are being humans and they just perform some tasks, either explicitly just labeling the data for supervised learning or performing some other kind of recognition. Of course, again, that's not the most exciting job. And well, first of all, it's not very interesting, and second, it's not well paid. So they usually, the people who do this over some online platforms, they want to finish as soon as possible, just get their money for the task and move to something else to get more money. So as I said, it's been over 10 years, closer actually to 20 years. Amazon Mechanical Turk was probably the first platform for this kind of microworks. It's still operating. And Yandex Toloka, I don't know if someone used it. Anyone used Yandex Toloka? Okay, yeah. So I'm not completely out of here. Someone in this section. Okay, and the problem is quality control. Because you can get the data back to you, but you have no idea if it was labeled correctly or, well, if there is a correct answer. For example, if you ask people to rate their aesthetic impression and they provide some ratings, but you have no idea what is right. I mean, someone likes the picture, someone doesn't like the picture, so it's hard to say. So you're basically concerned if they are putting the effort, if they care, and it's not very easy to quantify. There is a view of crowdsourcing data quality control methods. Well, I would even say that's more about data quality control methods in general, but it's the focus on crowdsourcing. Not really new, but still quite extensive. The most widely used methods nowadays are majority consensus and gravity. You can see them over there. And the majority consensus implies that the same task is performed by several crowd sources, right? And then you can compare their results and see if they match. If they don't, that's probably a red flag. You have to take a closer look what's going on. And ground truth is when you have, for example, 10–20% of correct data, and you inject it into the task. And then you see if someone, some labeler, some crowd worker, fails or performs incorrectly on these tasks that you know the answer for, then probably all the other data that is worker labeled is not good as well. But they imply redundancy, meaning that you have to throw out some effort for the sake of data quality control. If you ask 3 people to perform some kind of task for the majority consensus, that means that you waste like 67%, 2/3, right? You just throw it away. And for the ground truth, okay, 20%. Again, you have the right answers already, but you ask the people to label also this data and you pay the money. You think they did a good job. So there are also promising non-redundant, meaning that there is no overhead. You don't have to waste some effort and money. Yeah, well, that's basically what I already said. There's redundancy involved with these most popular methods. And also, if someone is interested, the non-redundant method. And the method I'm going to talk about that we propose is a non-redundant one. So there is no need to spend additional effort for the sake of data quality controls. We call it a distributional ground truth. I guess English translated to Russian as правдивое распределение, something like that, in the data. So we extract some data distribution from a trusted data set of some data that has a distribution. And then we compare it to a distribution in a tested data set. So we don't compare the data, which is right. We compare the distributions. And this way we don't have the redundancy. So we use the data set that we collected. There were students who labeled 500 user interfaces, basically screenshots of 10 pages. They labeled like buttons, images, pieces of text, things like that in the UI, in the interface. And then we had other students who assessed the performance, if they did a good labeling job or not. So these were these people formed our trusted data set. Of course, the students were also, there was their motivation, but as you'll see, they were still much better than the crowdsources. And the crowdsources in the Amazon mechanical turk, they formed the testing data set. So we wanted to kind of evaluate the quality. How well these people, we don't know, they are just in the online platform, it's anonymized. How well do they work? Can we rank them to give a good job of coherence based on their distribution, proximity to the distribution in the trusted data set? So that's the way labeling looked for the students. You can see they select elements in a user interface. And then that's how the verification for other students, they estimated how well their colleagues performed on the labeling. They, most importantly, provided correct and incorrect kind of estimations for every labeled element. So they were like 27,000 UI elements labeled, and for each of them, they provided correct and incorrect. And the percentage of the correctly labeled elements was the precision. And then there was subjective completeness. If their labels covered all the elements or close to 100% of all the available elements in the screenshot. So what we did next, these are our labelers, the names abbreviated. For each of them, you can see that we calculated precision and subjective completeness. These two metrics of the quality. And then we calculated the geometric mean in all students. And we ranked all the student labelers by the quality of their work, from best to worst. Well, because as I said, even the students, they had different motivation. For example, we can see that there was a person who had very high precision, close to 100%, but labeled on the half of them. So he was accurate, but better labeled. It happens. Oh yeah, and also we calculated the metric EUI, which is elements per UI, which we will use as a baseline. And so far, for the students, for the trusted data set, it showed no significant correlations with either of the quality metrics. That's how the labeling looked in the AMT, Amazon Mechanical Turk. And we got that made crowd workers who tried before the test. And some of the results were accepted by my German colleague, and some of them were rejected. And you can see these are the classes of the elements. And you can see that the distribution of the accepted and the rejected kind of work results are different. So we given us the exploration, right? So if we can distinguish the good results and the bad results, that's our goal. So again, we calculated the decision for the crowd workers as accepted divided by accepted plus rejected, in a similar way that we did before. And we found that the average precision was about 44%. So it's 2 times lower than in the trusted data set. So basically the crowd workers, they performed twice as accurate, right? That's accurate, right? Yes. And you can see also the elements per UI was 3 times over. So the students would care to label 3 times more elements. But apparently the crowd workers, after labeling 3 times less, would think that that's okay, that's enough for the task to be accepted, so they just stopped working. Yeah, and the correlation was between the precision and was also much higher than in the trusted data set. So basically, those who cared to do good work, they were accepted much more often, and they provided much better results. So then what we did, we ranked all the classes of elements by frequency. For example, most frequent would be depending on the accuracy. An image, a link, a button, and so on. So we do this kind of distributions. So there are 20 most expensive labels, 81 to 2020. And our best student label. So you can see that student label distribution looks much more regular and is closer actually to Power. You might remember S3T2, for example, right? As a case of Power. So we also compared to the Power label. And for the comparison, we used Kolmogorov-Smirnov test for 2 samples that can measure the distance between 2 distributions. And we used not Kolmogorov-Smirnov's criterion, but p-values, as you see. So yeah. So then we tested different sizes, different relationships of trusted data set to the tested data set. And we found that for about 7 to 18%, we have the highest R-square. Meaning that we know the quality of the output of the students, we know the quality of the output of the workers. So, and if we rank the p-values that characterize the proximity of the distributions, and then relate them to the work quality of the crowd work, we get quite a high correlation. Much better than, for example, the traditional metric, which is time of task. In crowdsourcing platforms, this probably is the most widely used metric. Well, the idea is if a labeler, a crowd worker, spends 1 minute on a task which is obviously requires, I don't know, 20 minutes, then there is no way that a good work was done. But in our case, we overperformed this metric quite well. And that metric was fit to power law. Actually, it was higher than the time on task, but still not high enough. The third baseline, number of elements labeled, actually demonstrated high correlation. But there is a problem with this metric I'll tell about a bit later. So, coming to the conclusions. Data is crucial, very expensive. And we want to spend our money and effort in the best possible way. So we don't want to kind of pay much for the data quality. We don't want to throw away some redundant data. So we proposed and tested the distributional ground truth method for controlling the distance between the distributions and the frequencies in the data using Kolmogorov's-Smirnov test. We found that it explains quite a lot this regularity, proximity of the distribution in the work quality of cloud labelers. We also actually published our previous paper on comparing to the power law, but as you saw in the previous slide, our R square is considerably larger than for the power law. And our second contribution is that you might want to look at the number of elements in the screenshot, but this metric is too easy to manipulate. Some malicious worker might just label very quickly some random areas of a screenshot if they know that we control for this. Because for the time on task, they already know if they want to maximize their effort, they open several windows, right? And they wait for 20 minutes in each of them. So the time on task doesn't work anymore because crowdsources also read research papers. And the metric that we propose, the distributions, they cannot be manipulated because a crowd worker might have no idea what is the distribution of the data because the crowd worker doesn't have a trust in themselves. If he or she tries to create trust in themselves, there's actually more effort than doing the job. So the split that we demonstrated works best is about 20 to 18. And of course, there are limitations for our method. First of all, is that there had to be some distribution in the data. If there is no frequencies or something like that, then we cannot build this distributions to compare. So that's something we're going to explore for what tasks it actually works. And second, that to consider a worker, we need to have enough data because you cannot infer a distribution from 10 data points, right? You need much more of them. So in our case, we needed about 100 elements at least. So basically, it means that we can use this method for some tasks that require some training so that the workers, they spend some effort and then perform lots of tests. We don't want the workers who just do one test and then do a time. But it's still a limitation. So I think that's it. If you have any questions, I would be happy to answer. Please.
Among the 20 dimensions of data quality you mentioned in the first slide, I think the most severe one is related to sensitive data. Sensitive. When you know that you have that you are missing some data in the data set, but you don't know what fraction of the data you're actually missing, and you may even not know what kind of data you're missing. Now, in general statistics, what you can do, you can use a sort of model based on prior knowledge to fill the gaps and somehow to take this into account later. But as far as I understand in machine learning, you just deal with data and that's it. True. So how do you think you can mitigate for missing data in machine learning?
That's an interesting question because we still didn't use theoretical publications on what is a good training data. For example, if there is something missing in the training data, does it mean that it's also missing in the real world? So then do we need it?
That's the issue of scientific research,
How
because you are looking for what you don't know.
Yeah, but that engineering, that's it.
All right. If you work with, for instance, census, if a certain portion of people do not participate, they're missing data. So you either, so they, of course, they exist, but for example, they cannot write, so they cannot participate in the census. But in general statistics, you know that these people exist, and you can account for them by using sort of model, because you have a certain idea how many of them are in your this area, for example, and so on. But in machine learning, you just don't think about that, right?
And it's not too much in machine learning, I'm not sure it's one conception, but I think it's simple. Machine learning scientists and engineers believe that everything is in the data. If it's not in the data, they don't care about it. And that's not what I think is good, but that's the way usually it is. Maybe in a while, there will be some models that you can think of this data. But so far, we didn't do that. And speaking about sensors, I talked to representatives of some metrology institution in my home city. And they thought that this kind of one of the applications might be that, for example, there's a submarine which spends a lot of time there, and they have it. And they want some machinery. And they want to know if this is working correct. But they cannot go up and connect to some kind of laboratory that can say, okay, that's fine. But if they have collected enough data in advance, they can calculate the distribution. And then they can compare their treatment data to the distribution. That would be not the same data, but the distribution is actually the same. Yes. So that's also one of the applications. It's not limited to machine learning. That's my response.
I have a question. So I understand correctly, you have one experiment when one team outsourced perform something, right?
We had a team of our students,
Just one.
whom we trusted, and we had external hundreds of people who don't know.
Doesn't matter. Just one team.
Yes.
And from one statistical experiment, you make some general conclusion. How it's possible in general?
Well, statistics
One team performs such, another team maybe perform better, third team perform worse. You just make one measurement and say that as a science, you can do some conclusion. Sorry, it's just students work for non-parametric statistics. They don't understand completely the idea. Statistics, by the definition, is a science about the repeatable things. They should be repeated.
if someone
You
wants
have to have many teams to compare. What you show that such particular team works better or it doesn't matter, but one team. How you get generalized that?
we show basically that we can infer a distribution from a trusted data set for the test and compare it to the distribution in the tested data set. And that the result of the comparison makes sense in terms of data quality. Of
Makes
course,
sense for such particular measurement.
of
Nothing.
course, every kind of statistical experiment is limited. And in our case, it's limited
No,
to the UI labeling. That's exactly what I'm saying.
what is data quality for you? What is it in data quality for you?
Data quality in this case was operationalized by two dimensions, precision and subjective completeness.
Data quality and data high quality is fit for its intended use in operation, decision making, and planning. In other words, data is high quality if the usage is good. We never talk about the usage. It makes this a measure, mark button, and so on and so on. You just measure the performance. It's not the data quality.
Well, I partially agree with that because
It's not dependent.
yeah, well, I'm not sure. But our assumption, of course, was that if the data is more complete and more precise, then it's better for the usage. It's not always the case, but I think that's our assumption. Thank you very much.
Yeah, as I understand, to put the product report to the synthesis, you use you need to actually very high quality set that you build with your processing, and it seems like chicken and egg problem. So I think the most maybe a misconception, but I think the most interesting question is how to actually build this trusted team to build this high quality starter package.
Well, that's a good question, but I wouldn't say that we need a too high quality. Because you can see that the precision is 89%, and this is 78%, so it's not exactly 100. The students were reasonably motivated, but not perfect. So that's an interesting question, how trusted it needs to be. But these were just regular. I think you had a question.
Я, ну, это вопрос. Скажите, а вот эффективность таких методов естественных форм в Китае, на каких-нибудь массивных пробах?
Я еще не пробовал, потому что мы работали с данными, которые собирались с участием людей, там обычно их не очень много, потому что дорого. Вот как раз вот, когда отвечала на вопрос про распределение данных в каком-то работающем, распределение в данных, полученных с какого-то работающего оборудования, вот там действительно, да, но мы это пока не проверяем. Я предполагаю, что там, вероятно, будет результат, потому что есть такой даже пост про межлабораторные сравнения. Вот. Но в явном виде там вот такой метод не описан. Вот. Но по сути идея там в том смысле, что есть вот, значит, референтная лаборатория, которая данные всем готовы давать правильно. Да? Ну и, соответственно, это тоже референтность. Знаете, это тоже очень интересный вопрос. Ну, мне все время кажется, что новизна этого хоть не сильно должна быть высокая, потому что нельзя сказать, что супер оригинальная. Но ни один рецензент никогда не говорит, что он где-то это уже читал.
Просто я посмотрел последний слайд, где ограничения. В принципе, я тоже работаю с большими данными перспективы, но для нас это не.
Ну, давайте с вами пообщаемся подробнее, я с интересом обсужу.
Мне просто интересно было бы, можно, потому что там большие действительно, да?
Да, конечно. No more questions. Thank you very much.